Next up, we've got this guy. This is the Asus ProWS WRX 90E Sage SE motherboard. So a couple of things about this. One, it's really heavy. for a motherboard, I mean, this thing weighs about as much as the power supply that's going to go into this piece of equipment. A couple of big advantages to this particular motherboard. One, massive amounts of PCIe lanes. So PCIe 5, fastest standard that we have on common motherboards right now. We've got 128 lanes in this particular motherboard, all going directly to the CPU. So in classic boards, if you were to start loading up all these components onto them, they might have like 24 lanes, 32 lanes. They all start fighting with each other, trying to get all their traffic down the highway to the CPU. Not this guy. This thing's built out with tons of infrastructure, makes it very easy for lots of data to go flying all over the place. And that's going to be critical, especially since our two GPUs don't have NVLink. So you take one RTX 6000, this thing's pretty awesome. It's got 96 gigs of VRAM. It can run at 600 watts. I mean, you can move a heck of a lot of tokens with one of these. But unlike the old 3090s that had NVLink, and unlike some of the server grade systems that are going out now, H100s being like an example, there is no native way, NVIDIA didn't give it to us, to be able to combine these and have unified memory between them. So I've got 96 gigs over here, 96 gigs over here. That doesn't make a perfect 192 that's just moving at the same speed as the GPU. So this is where the motherboard kind of comes in. One of the most important factors that you're going to encounter, since these two GPUs can't natively just talk to each other, is bus speed, PCIe lanes, how fast data can be essentially transmitted back and forth between the GPU, the CPU, back to the GPU again on bus traffic. So when we try to combine these two things together and we start getting them to talk, like if we take a really big LLM and make it share the two GPUs to be able to host itself, the biggest factor we're going to encounter, the biggest bottleneck, is going to be PCIe speed and how much data we can move how quickly up and down those lanes. So with this particular board, having 128 lanes of PCIe 5 is pretty insane. There really aren't any comparable boards that I can think of off the top of my head that have similar capabilities. So what you should be thinking about for that is each one of our graphics cards gets a full 16 lanes at PCIe 5 speeds, roughly 64 gigabytes per second of traffic going out, 64 gigabytes per second of traffic going in, so roughly 128 gigabytes per second total bandwidth. So each one of these GPUs gets roughly 128 gigabytes per second of bandwidth that it can use to fly up and down the PCIe bus. So on traditional boards, you plug one of these in, maybe that first one would get that bandwidth, you plug a second one in, and now they're starting to share and struggle with each other. So with this particular board, we have so many lanes of so many different kinds that we can plug in all of our stuff and nothing's fighting itself. It's all got its own independent information superhighways going back and forth to the CPU. So really important thing not to neglect is PCIe bandwidth speeds, individual lanes that are available for cards. If you're going to bring this much hardware together and you're going to do all this stuff, this isn't where you want to cheap out. The other thing worth noting, which is really cool about this board, is it's got remote server support. So it's got a lot of features that a commercial server would have. You can remote access this thing, remote boot it, do all kinds of different things that you wouldn't be able to do with a traditional board. And also, it's got native support for dual power supplies, which is something we're going to be using later. So no weird third-party connectors and things like that. The board comes natively supportive of dual power supply setups. So that's going to be awesome for us. But that's the motherboard.